let me first park on this beautiful ion trap picture. It looks very gold because it is like coated with pure gold. In fact, the gold you coat onto your ion trap, the less the noise there will be for your ion trap operation. So, you know, ion trap quantum computer's trap all looks very beautifully golden coated. Yeah. So today's presentation, I will mostly talk about the hardware, how does ion trap quantum computer works. Really all just very basic physics, very basic science behind how the quantum computer work together as a system. And then I will also try to introduce some of the newest development at IonQ and in the academia to push the boundary of ion trap quantum computing. And finally, I'll talk about some, just a very, very tiny, teeny tip of the iceberg about how quantum computers are used to solve real-world problem, and what are some of the research, some flavors of research along those directions. So yeah, I hope you'll be having fun. So first, a disclaimer, I mean, the company require a typical disclaimer of different style, but I mean, I just don't like that style. It's very corporate, very legally correct, but sounds very boring. So I put a lot of cute animal here to make the vibe more friendly. But anyway, what I'm saying is still the same thing. All the material appear in the presentation. They're pure academic material. I just know them and I would like to share with them. None of them is like secret message from IonQ. Okay, so please don't listen to my presentation and inform your decision of buying the stock or not. Right? It's not good. Okay, yeah. No secret, no secret. Yeah. All right. Just to chill, like one of those animals. Yeah, just chill, enjoying. Okay. So, there are many different kind of quantum computers out there, right? There are QEra, there are IonQ, D-Wave, and IBM, just to name a few popular modalities out there. Yeah. As you can see, all of them looks very similar, right? Just a black box. You may wonder why. I don't know. It's kind of cliche, right? It's like the trend, the fashion are all similar. People like to dress the same. The quantum computers like to dress themselves the same too. Well, but unlike a human, right? We're all the same inside. Quantum computers very different inside. If you open one of those black boxes up, yeah, you look inside, you will see all different kind of architecture. Looks very, very beautifully different in a beautiful way, right? For example, let me see if I have my laser pointer. Is this my laser pointer? Oh, laser pointer. Okay. On the left side, this is an ion trap. It's a miniature version of ion trap quantum computer, meaning every component is much more shrink to reduce the size and the footprint of the quantum computer, right? And in the middle was the very first generation of ion trap quantum computers that we used. It is one of the ion trap quantum computer I built and designed and experimented with in my PhD at University of Maryland. It's one of this kind of quantum computer. And you have photonic quantum computer that looks like this. This is one of the quantum computer from USTC China. It's a picture they took from their lab when they did one of the first photonic quantum supremacy experiment that was published, I think, on Science, right? And this is a silicon quantum dot quantum computer. It's a piece of diamond with MV center on it, and it's a popular choice at some point to try to build a quantum computer out of this, right? And there in the middle, there's this neutral atom quantum computer. Like you have Code Quanta, you have, I believe, Quantum Machine, and many companies are also doing this. And on the rightmost, there's a superconducting quantum computer, right? I mean, if you ask me, I don't know, maybe the one on the bottom right doesn't look so good compared with the rest. It's just design thing, maybe. Yeah. Anyway, so this is a table as of 2022. of different performance or different feature of quantum computers. If you look at a spec sheet, you will see they're quite different. People like to claim each of their have their own advantage or disadvantage. So it's something people like to ask about, like what is the best quantum computer, right? As of time 2022, this is their performance, and people like to say, for example, neutral atom and trap ion has long coherence time, and then you have gate speed. Superconducting qubit has short coherence time, but the gate speed is fast, right? All this kind of difference. So, but I have my oversimplified top-down view. I think this slide is only reserved for academia presentation, meaning for audience that has an interest to learn the true physics behind the quantum computer instead of trying to figure out which company stock you should buy. The reason I'm saying that is I think from scientific perspective, the difference are it's almost like whatever you are facing with two biggest choice, and whichever choice you make, you will be facing its own pros and cons, right? For example, qubits. We have natural qubits, neutral atom, trap ion. They're natural qubits, means these qubits are there. Our computation is made on the internal electronic energy level of neutral atoms, either neutral atom or trapped ion. It is that electronic energy level. So it's already there. We just need to trap them, right? But then you will have the challenge of trapping them. So trapping them is not trivial. You have to have the vacuum, you have to have your electrode. In neutral atom, you have to have your laser system to reliably trap them into array. But then if you decide to fabricate them, if your qubit is synthetic, then you don't have to fabricate them. You don't have to trap them. You can fabricate them just like superconducting qubits. You can make the qubits wherever you want it, form them into an array, but at least back in a few years, how do you make the fabrication reliable? How do you make sure each of your qubits have the same performance, have the same intrinsic frequency that you can interact with, was a challenge. I think they have improved by a lot recently, but still a challenge, right? And you also have the choice of choosing from the elements you choose to make the qubit. What is the qubit, right? For example, you can make your qubit some easy to interact with quantum state, right? For example, ion is charged. If you want to use the motion of your ion, quantize the motion of the ion as your qubit, you can do that. But then the coherence time will be terrible because that state is easy to interact with. It's easy for you to interact with. It will also be easy for the environment to interact with, right? So if you choose a state easy to interact with, typically you have better gate speed, but you will have more noise, so less coherence time. So that's really just a design choice. But today we'll be focusing on the ion trap, so you don't need to worry about this too much. But overall, I think this is some helpful insight because people like to think about what is the difference between modality, which modalities is the best, right? So you have to know the physics, you have to balance them off, and have your own understanding of what is the better technology. Okay, let's go through a quick history of ion trap quantum computers, right? In my view, I like to make it a little bit fun and maybe unnecessarily fun. I would say it dates back to when people realize when they burn different material, the fire appear to have different color, right? For example, lithium, here, as you see, lithium, they burn in purple color. Sodium have this iconic yellow color, right? If you sprinkle some table salt onto a fire, I don't know if you play with that when you were a kid, or maybe even nowadays, no, never too late to play with. I played that a lot when I was a kid. dust of salt into fire, you will see the yellow spark from the fire, right? This color are really just like excitation from energy level, right? From a lower level to a higher level. And this excitation from discrete energy level give you spectrum lines that are the color. And the spectrum line literally tells you there is a very stable energy level, two-level energy state. You can use that to make quantum state, right? And once people realize those are very stable energy state, that any oscillation between them can be very stable, immediate thing you realize is, well, we can use this to make clock, right? That's the first pursuit. People realize quantum technology in this way can be used to make very, very accurate clock, atomic clock. We use them nowadays in satellite. We use them in submarines underwater. GPS is based on this technology, right? It's a backbone of modern information technology, right? It won Nobel Prize at some point. And then later people realize if you trap the atomic particle, your atomic clock will be very, very accurate. That's because motion creates broadening of your spectrum line, meaning it will create decoherence. Broadening of the spectrum line is equivalent to decoherence, right? So with ion, people start to make ion trap, and people start to make more and more complicated ion trap. So to the point, at 2015, we started to make this kind of blade trap with segment of electrodes that allow us to adjust the electric field, that you can trap the ion as a chain like this, right, to do quantum computing. And later, the technology, the field shifted to use this kind of microfabricated surface trap. So nobody needs to use their hand to build a trap out like this. You can just use something very similar to modern day CPU, GPU, microchip fabrication technology to print your ion trap, to allow many, many more, like hundreds of electrodes arranged on that surface trap, and of course coated with gold so it looks nice and luxurious, yeah, to have better control. So this is a current technology. This one is a trap IonQ used to test its barium ion technology and released back in 2024, right? Okay, so that's the history. So ion trap quantum computing is really based on this very, very long train of history. Since the very early days, people started to experiment with ion, with atomic physics, with laser technology. So we have all the tools that comes from 60 plus years of technology advancement. It's a very beautiful and school of long history. Yeah. So how do we trap ion? Yeah. Next, I'm going to just dive into some of the core technology pieces of how you trap an ion, of how you do gates. So how you trap an ion, right? If you look into Maxwell equation, there is this thing, it's called Earnshaw theorem, but it's like a two-step derivation from Maxwell equation that says if you have a space, if you want to use a static, like a stationary electric field to trap a charged particle, it's impossible because any electric field goes into a space, it has to come out of the space, right? It cannot all point into a single point into that empty space. So you can trap the ion at that point. So what that means is you will have, the best you will have is this kind of saddle point, right? You can trap the ion along this two direction, but on the opposite orthogonal direction, it actually repels ion, right? So with this fact, how can we, you will never be able to have a hole like this that you can trap like a golf ball in the between. But so what can we do? I mean, this animation has been playing here for so long, so hopefully you get the idea. The idea is as long as you make the saddle point rotate and the rotation frequency, speed, and the mass of this ball satisfy a certain relationship, this ball will see effectively a trapping potential. It will see a hole like this, right? Let me say it again. If you have a saddle point like this, it won't trap, but if you make it rotate, it will behave like a hole on the left, and the golf ball will be trapped in there. And essentially, this is exactly how we trap ion. We don't rotate the trap physically. We don't. You use AC electric field, microwave field of about 20 megahertz something to rotate the electric field. It will trap your ion in there. Okay, so this is ion in picture, right? And modern days trap, for example, the one on the right, have so many electrodes print on it. You can trap your chain of ion and split them up, put them back in any way you want. So that's how you trap ion. When you trap ion, you get your qubit, right? So the next thing you need to do is to apply operation to drive the internal state of the qubit. It is very much similar to how you do the fire trick. Again, this is my favorite analogy. I hope you also like it. Basically, when you burn the material, it gives you specific light. That's the transition between two specific energy levels. They emit the energy that corresponds to the frequency difference of that two energy level, right? So they emit such energy when they drop from higher level to low level. If you shine the light of that exact same energy back at them, you will excite them from low energy level to upper energy level. And in fact, if you do that coherently, what you have is this kind of physical effect called the Rabi oscillation. It's a coherent oscillation of population between the two energy levels when they're coherently excited by laser field, by electromagnetic field, right? So if we have energy level, if we have two levels, we call one of them 0 state, one of them 1 state. Using this laser field to drive them would allow us to coherently change the state from 0 to 1. I keep repeating coherent. Coherent means you drive the transition that keep the phase stable and pristine. That's how you do quantum computing, right? So, and how you detect the qubit. It's very similar, again, the color trick, right? Say you have a qubit in the 0 state as f equals 0 and 1 as this f equals 1 state here. You can just shine the light of the color of the frequency that matches a specific resonance only with one state, right? And then that state, if your qubit state is in 1, it will resonate with this light you shine on it and the sparkle light from it. It's almost like some kind of point in the air that would give out light that would sparkle, right? But if you are in the 0, you are not resonant with that frequency. Even you shine light on it, it remains nothing because it doesn't give out light, right? So you can't see anything, and we call that dark. If the ion resonates with this laser you give to it of this frequency, it will behave like a bright spot floating in the air. That's what we call bright. It means if you measure it that way, it's 1. Yeah, and you can use this PMT array to collect the information and detect and decide if the qubit is 0 or 1 this way. Yeah, what you see here, it looks like a line in a black circle. It's actually just a fiber like interface, and here you have 33 different channels for 33 different fiber input. It allows you to do individual detection. That's one of the old technology we used. I think it's still the one that have been used by many in different architectures. Yeah. And to initialize qubit, meaning you want to be able to reliably put all your state into 0, right? If it's atomic state, it could be in 0, could be in 1. You want to be able to reliably put your qubit into one of the two states, right? So we typically choose to initialize the qubit into 0. We use this technique in atomic physics called optic pumping. Essentially what you do is you drive all the transitions between all the possible transitions of the one state. So the population is jumping crazy among all those states, right? But all those states have the same possibility to drop back into 0 or 1. So the ion population, when they are excited, they can go to 0 or 1. But you only drive the population out of 1. So after some time, your population will all be accumulate on 0, right? That means you will be prepared your qubit perfectly in the 0 state. So that's the idea behind optical pumping. And for ion trap, that's how we prepare our state, our computation to initialize the qubit into 0. Next, you can't just do computation by only controlling each individual qubit, right? It's like if you have a classical computer, but you don't have a data bus to interact different bits. Bit have to interact with bit to make computation, so is quantum computing. Qubit have to interact with another qubit to do quantum computing, right? So again, you saw this animation on the left bottom. This is in a nutshell how we do quantum computing with trapped ion. The trapped ions are in the chain and they're all charged, right? So they really just behave like this toy. We call that Newton's cradle, is this toy. The ions, they're pretty much more like a chain, like a spring-loaded chain of metal balls. But the point is the motion of each qubit is related to another qubit. So what you do is you can use laser to push one qubit. If you push the qubit in the right frequency, you will excite the motion on that qubit, on that ion, right? And if you just give it a little bit less of energy, so it's just by a slightly little bit, not enough to drive that motion, the nature is magical. It will compensate for that of lack of energy by taking some from the internal state of the ion. So the ion will change from 1 state to 0 state, but that additional energy will transfer together with the laser you push it, transfer into the motion of the ion. And because the motion of the ions are shared, so that motion is gonna come to here. Now you have the laser, you have that a little bit more energy. That energy plus the laser energy can go back into the ion, right? To transfer to that energy back into the internal state energy of the qubit. So this population would go back from 0 to 1. With this way, you essentially are capable of converting energy from putting energy from one ion to another ion. And this is the same for all the computation. Whenever you can move energy, basically a well-controlled, coherent energy can be used to represent information, right? So if you can coherently transfer energy from one qubit to another this way, you are capable of doing 2-qubit gates. So that's my way of explaining how you can do qubit gates without going through the math. Basically, it's like this motion to convert energy from one to another that allows you to do gates. Right? So there are actually quite many choices for ions, right? We have the whole elements table. I don't know why some of them are elements for them, some are people's face. It's not a, I don't know. Yeah, but anyway, they all have different color, they have different energy level, but we have our favorite energy level, right? Let's see. There are many considerations. The energy levels in general are very complicated structure, right? For a long time, people have been choosing this ytterbium-171 ion. That has been the choice of IonQ for a long time, right? There's many advantage of this specific species. The biggest advantage, I think, is this 2 energy level that we choose, 1 and 0, to make our 2 qubits. They are typically the transition between these two are typically forbidden. So you can't just use a simple one laser or electromagnetic field to drive this transition. This way, the population can stay on one for a really long time without any disturbance. So it is a very good state to store your information. And also, it has a complicated energy level that are not really shown in complete here that would allow you to do all the necessary procedure we mentioned above: initialization with optic pumping, and detection via state-dependent fluorescence, right? And all those things. And you have this forbidden transition, and the forbidden transition actually can be bridged using an auxiliary state with commercially available laser. So now you don't need to have a special laser to tune with special frequency. You can just buy one from the market and you can plug in and it will very nicely. And this laser is very popularly used in semiconductor industry. It's a lithography laser. So very reliable product. You almost, it just means so much reduction in trouble. If you imagine yourself being a student working in the lab, you know, like anything you have to do specific tuning, it's not reliable. You have to do many things to make it function anytime you want, right? It's very annoying. So this is a huge advantage. And another thing, and like we said, it have a long coherence time because of this forbidden transition. What's more? Okay, shit, there's no more. Okay, well, yeah, all right. But then there is also an issue with it. The issue is this transition is UV. It's very UV. And the UV is an unfriendly frequency, right? If you go into the bright sun, the UV would make you look very black, yeah, like I am, yeah. And you have to protect yourself with sunscreen, otherwise you get sunburn. So people get sunburn because UV. Turns out a lot of elements in your experiment in your quantum computer also get sunburn from UV, like the mirror, right? And even laser crystal, they get UV burn. And when they get burned, the performance drops. So that has been an issue. But other than that issue, it's almost a perfect like ion species, right? So with that, let's just take a look at this very beautifully crafted animation to see what ion trap quantum computer operation actually looks like. It really just looks like this, right? You have a beautiful golden trap, and you have particles floating up there, trapped by the electromagnetic field, and you have laser carrying your information and shine on each of the qubits to put information on them, thus running your quantum circuit, right? So maybe let's talk more about the future technologies, right? IonQ has been running this, what do you call it? Laser-based ion gates. And I don't know if you guys heard, you guys probably heard IonQ recently acquired Oxford Ionics, which is a company focusing on doing pure electronic driven gates, right? So what is that? They published this paper, so it's an open thing, right? What you do is here we use laser to drive this, but you can use microwave to also drive this transition directly, right? It's a microwave of special property. A beautiful thing about microwave is if you have a wire that is printed on your trap that used to conduct a microwave, you can have this thing called a near field microwave. That basically is a microwave that only exists in a very short distance, within a short distance of these wires you have here. So you can just have this wire to deliver, you can just imagine it to be a laser at this point, that you can deliver with the wire to anywhere you want. And you can move your ions in and out of that wire to do transition. So no more UV issue and no more constraints in that light have to travel in straight line, right? Ideally straight line, actually even more complicated. And you don't have to bother, you don't have to suffer of the noise laser accumulated please. What? Okay, well, turns out, yeah. And when laser pass through the air, it accumulates the noise from air turbulence, right? But now you have microwave wire conducting them. So the laser is not even there to accumulate noise, and also you don't have the alignment issue anymore. So this is really a beautiful technology that is super powerful for scaling up to make your quantum computer perform better, right? Okay. Now back to a few things of IonQ. This is probably a slide that needs to be updated. IonQ has been having a portfolio of systems that are engineering and designed generation by generation to have a very clear mind of improvement, either in qubit counts or either in qubit choice, right? For example, you see from here, from ytterbium to barium. Barium is the qubit that behave almost like ytterbium without the disadvantage of UV light. So if you work with barium, there will be no UV burn to your device, right? It sounds magical, right? But barium itself is radioactive in a very bad way. Like you literally get, okay, not literally. If you have a lot of barium surrounding you and you sit next to it, you get cancer after some time. That kind of radiation, right? But in reality, specifically because IonQ is very good at engineering, and if you have a company that can invest in laser protection, just like a nuclear power plant, right? I mean, this is by no means as any way extreme as that. You can protect, shield the product from any tiny small amount of radiation, right? So with proper engineering, it's safe, and we can harness the advantage that can be provided by this species. And to use a quantum computer, it's not enough to just have the hardware, right? You have to have the control platform. Many of the algorithms we have these days are hybrid quantum algorithms like VQE, like QoA for optimization. Many of the popular ones require iterative optimization. So we also have software and a cloud stack to empower that. And at the top level, you also need to have the algorithm that you run. So yeah, IonQ has been collaborating with many companies developing quantum algorithm for different problems, right? And here is our hybrid platforms. And actually here the slides is showing as a kind of like a result from last year that show how much you can improve the performance by just improving your software. For example, the most straightforward way to see this is you have quantum computer, right? You have quantum algorithm. For us, you have to convert the computation you want into laser, and the laser deliver to our system to run your algorithm, right? So the speed your algorithm can run is in some way limited by how fast you can write your algorithm into laser sequences. So by upgrading the software, we have achieved the 46-fold improvement in how fast we can do algorithms. So pretty good, right? And there are many things, right? We talked about the barium, change of ion species, give you less UV burn, but give you some cancer. No, that's a joke. With engineering, you don't have cancer. And also, very impressively, we have to make the ion trap smaller, right? Here, this is the latest ion trap package. Inside this package is that golden trap you see. Years ago, okay, well, that's too far. I'm not going to jump back. Let me see if I have other stuff. Okay, I don't. Okay, years ago, the traps are as big as a fridge, like literally a home fridge you have in your home to put your ice cream, to put your milk, right? So we have went really far away, really long way to reduce the whole thing down to this size, almost not much bigger, just than a quarter US dollar coin, right? And with this reduced size, the whole quantum computer can just be made much smaller, consume less energy, and much reliable to work with. So it's a very big part of it, right? And also now to scale up quantum computer, we also have to connect systems together with other systems, right? And our IonQ's approach is to use photonic interconnect to connect systems together. And in the past years, we have demonstrated how to convert information from ions in one trap into photon and use fiber to convert into information back to the ion on another trap. All right. So with that, that will be concluding my talk today about the hardware. Yeah. Let me take a pause, see if people have questions, and next I will go to a very quick rundown of the algorithm. Just two very simple algorithm we've been doing with some customers or just internal development that we think that the field in general think are good candidates for quantum application. Okay, questions? No questions? Okay, no questions. Wow. No question means no problem. Smooth. I hope you understand everything. Yeah. Okay. Algorithm. All right, let's just jump in and skip the summary, whatever that is. Right. The first thing I want to introduce about is hybrid algorithm. One very specific thing we did about hybrid algorithm or generic variational algorithm. The variational algorithm is really at the backbone of many quantum machine learning approach, right? At the core of it, you have a quantum circuit with many variational angle to it, right? And you want to adjust the angle of these gates to allow your computer, you want to adjust the angle in some data-driven way or just optimization-driven way to get some of the best answer out of it as you measure it, right? So it can always be converted. It can always be looking as a optimization problem that you want to adjust this gate's angle to find the global minima or the global optima, right, of your energy landscape. But there is an issue called the barren plateau. That means when your system is large enough, when you have many of this angle, then the gradient that many of the optimizer like we use nowadays will not see any gradient. And if you don't see gradient, they don't know where to take the angles to, right? So you won't be able to optimize it anymore. And another thing is you may have many local minima. So when you have many local minima, your optimizer, when you get to there, it traps there. So, and these problems are not really there or only there to some extent in classical machine learning, right? That's why the classical machine learning neural network has such a success on one hand, because the gradient seems to be strong anywhere, no matter how deep it is, as long as you design your neural network properly. On the other hand, there is this thing, basically they think there is no such a thing as easy to trap in local minima, because it's like I mean, sure, you can't prove you ever on global optima, but even you on local minima, your model can provide good utility, meaning the difference maybe just be trained to 99.5 accuracy versus 99.7, right? So that's a key of its success. But those doesn't seem to be there for quantum. So people have realized in quantum, what you have to do is you have to introduce a lot of inductive bias, meaning you have to introduce the symmetry of the problem into the design of your circuit. And the inductive bias, just like in classical machine learning, is really there, right? At the very basic level, you have fully connected neural network, but you know, nowadays, who use fully connected neural network to solve big problem? It's always very complicated architecture, built in with smartly designed, with carefully and insightfully designed architecture. For example, convolutional neural network, right? Back in 2015 something, when the computer can process image, can process video very effectively, and that was very impressive. It's due to the introduction or utilization of the convolution neural network. It basically says it's a neural network structure that says there's a symmetry of translational symmetry, right? So if you see a car here, it's also a car here, and it's also a car here. Wherever the car is, it doesn't affect your computation, right? And you also have a recurrent neural network that is in the early stage of translational, of like computer translation, right? It means if I say an apple at the beginning of my sentence, or if I say an apple at the end of the sentence, it just means apple, right? There's no difference. So it's like a different kind of translational invariance go through your sequence. And in fact, many people think when you go to the tutorial on what is the transformer, what has been the attention mechanism that empowered, that by large part empowered the latest AI advancement, that's the core part of it, right? So a lot of it, if you look at it from the very high level, I mean, I'm not an expert in machine learning, classical machine learning, so I don't want to say in too much detail. But if you look at a very high level, this inductive bias, the symmetry that you build into your model is very important. So why do I spend so much time on that? It's because there is another very popular neural network structure called graph neural network. That means if your underlying data or your problem is actually on a graph, there are many symmetries it has, right? For example, the graph on the left you see here is the same on the graph on the right. So how do you design your model to do this, right? And classical graph neural network has its issue. So we designed this quantum neural network structure, this quantum circuit that is inspired by the classical neural network, by the classical graph neural network. The key idea behind the classical graph neural network is you do the same operation on each of the edge, right, to preserve the symmetry. So when you translate your notion of the edge, it's not affected because those operations are the same to begin with, right? So we do the same. We do the same operation. We use the same message path. We call like quantum operation. We call it message passing quantum operation on different of the gates, on different of the pair that's representing nodes in the graph to preserve the symmetry in a similar way. And after all, we still have to optimize each of the angle and get a result out, right? But with this structure, we're capable to capture the symmetry. And with that, did we show result? Okay, we haven't shown result. And their advantage, why you would do this with quantum graph neural network? Well, there's a few issues in classical neural network that are known. One is the classical graph neural network has representative power expressibility bound that is known to be limited. With quantum, people have shown in this paper, that your quantum neural network designed that way can have higher expressibility, meaning the category of function it can represent is larger. So in that sense, it's more powerful, right? And quantum also have this quantum kernel advantage. That means you may be able to train the neural network with less data and give you better generalization, give you a model. It's a highly symmetric onset, so it has less barren plateau we talked about previously. And it also could reduce the time cost on QPU, right? And you have this bottleneck issue with classical neural network. We don't know if this is true, but there has been hypothesis that quantum graph neural network can potentially reduce the information bottleneck issue on graph neural network, right? Okay, so we use the graph neural network to test some actual real-world problem that we collaborated with actually a research division of Hyundai to work on this point cloud classification problem using quantum computer. You know, we observe with the quantum graph neural network, you are indeed capable of predicting those bounding boxes of your 3D point cloud. Of course, yeah, you know, take it with a grain of salt. We had a lot of classical post-processing. Quantum computer is still very weak. What you see here, the bounding box is not directly thrown out by quantum computer. It's a lot of classical pre and post processing, right? But still, we observed, at least in simulation, that if you see here we have set 1, set 2, set 3, set 4, they are point cloud of different sizes, right? So it's a model trained on point cloud of same size, but applied to model of to point clouds of different size, right? So because you trained on the small size, naturally you would expect the performance to drop as you move to larger point cloud, right? That's what you are observing on the classical side, you know. But if you see it, the quantum graph neural network seem to show better generalization, that it is capable of like sustain of like keep its performance at more or less a stable line, right? Even though of course the starting point is lower, but it doesn't suffer from like this size induced drop in performance that indicate it may have better generalizability. And also we tried this on both simulation and on QPU. You see that the QPU result indicates the quality really this algorithm is really quite noise resilient, right? Okay, let's talk about another thing, optimization. So, okay, I'll flash really quick to save some time for question and discussion, hopefully. Optimization has been another, like, it just has a lot of demand in quantum computing. I don't know, you can take it with a grain of salt of how much you like optimization algorithm. To be honest, I think it's a great direction, but I mean, it's just optimization, right? So it's not really that fun, but it's a good thing to study because there are many demand in industry, right? And the most popular algorithm is probably called QAOA, right? I think nowadays everybody know QAOA. If you want to make your first quantum algorithm, the first algorithm you should make is definitely QAOA, right? You will have some good result and you will have fun. Well, QAOA, you have to optimize those angles, so you also suffer from the baryon plateau and all those things, right? So what you can do is you can change to this quantum imaginary time evolution. So it's basically very similar to QAOA, except you don't optimize this angle. You calculate what those angles should be according to the imaginary time evolution formalism. The imaginary time evolution, so you know, in the actual world, quantum evolution corresponding to this Schrodinger equation, right? And you have real energy, and the real energy gave you a phase in your state, right? It accumulates phase. That's quantum evolution according to Schrodinger equation. But if your energy is a imaginary energy, then that will be corresponding to a decay factor. The higher the energy you have, the stronger the decay, the state you will have. What that means is if you prepare your initial state into a superposition of many possible combination, we call quantum superposition of many states, right? Those states with higher energy will decay faster, exponentially faster, right? And then if you run this evolution formalism, in the end, what you will be left with is ground state. If you have ground state in the superposition to begin with, you will be left with that after some time because all the other states decayed exponentially fast, right? And using this formula, you can calculate what those angles should be. So it allows you to not doing this optimization that in many times really just doesn't work, right? Okay, so I mean here are some more math detail about how the variational time evolution, imaginary time evolution goes, but I will skip that because I promised we're not going to do any math. Now I just want to show you some of the application of this imaginary time evolution to some problem. One of the problem known as max cut problem. It's just like that. You have a graph. You want to split the graph into two sets of black and white nodes, and you want the edge that is cutted by having two of its adjacent node one white, one bright, one white, one dark to be maximized. So you want the maximum number of edge to have to be connected to nodes of different color, right? In this case, 1, 2, 3, 4, 5. You can cut all the edges, right? This is a NP-complete problem. It's computationally known as very hard to solve. So you can use imaginary time evolution or variational time evolution. Sorry, you can show that your energy indeed will drop, and in fact, it dropped to optimum here. You can solve this problem effectively. We also apply this to different problem and compare it with QAOA. You can see as iteration goes, the QAOA really didn't go much, right? Just because it's probably barren plateau, or it may be some issue, or maybe our baseline test is not good enough. But the point is, if you use imaginary time evolution, yeah, your optimization will go well. Do I have other slides? Yes. And we also apply this to our QPU to test it, right? And here, different line, they correspond to different problem sizes. And we see you can always optimize it effectively to global optimum. So it's a very interesting algorithm. I feel I just flashed through it very quickly, but I encourage you to look for more detail in this paper. I think it's a very interesting technology and technique, right? Or technique, especially if you're interested in QAOA. I think this will be a very powerful alternative trick if you can play with to add into your repertoire. So yeah, with that, we finally come to the last slides. A full page of orange with thank you on it, and this slides conclude my presentation. So thank you for your attention, and we can park here for questions or discussions. Okay, we'll see. Okay, so we have one questions first. What was your reason you decided to specialize in trap ion quantum computing among various platforms? Oh man, what a good question. Um, okay, I mean, I don't have a heroic answer for this. In reality, when I first started my PhD, I was doing some high power laser stuff. And I was very sad. I was very sad. I don't like the high energy laser. I think the field is researched to death in some way. I mean, if any of you are interested in high energy laser, don't take my words. I'm joking. Well, but that's the way I felt. So I wanted to change my direction. I remember I was reading a sci-fi story about a quantum computer. It's totally wrong, you know. It doesn't even give a right scientific. It says quantum computer can find an element in an unsorted database with O1 efficiency. That's just a nonsense, right? The fastest we know, the Grover search is O square root of n. So much compared with O1, it's nothing. But you know, that's something I learned by reading sci-fi. So I was like, so I feel I really want to know more about this quantum computer thing. And I was at UMD, so Chris Monroe was a professor back in time there. And one of the afternoon, I just walked into his office, and I don't really know why he decided to take me into his lab, but but he decided he would take me into his lab, you know. And I don't even know who's Chris Monroe there, you know. I just look at the university website of professor, and I saw Chris Monroe have the best looking picture and best looking group picture, and I was like, yeah, let me give it a shot, you know. So this is a good question because it really makes me feel like I don't think I have that much control over it. It's not that insightful decision. It's just happened to work out. Okay, question next. Are there any ongoing research or method to reduce the gate time in ion trap? Yes, yes. There are quite a few. One thing we talked about, the microwave, right? If you have the microwave technology, you can use this specific microwave field called, I think, magnetic dipole transition to directly drive that Q level. So previously, it's slow because the direct transition is forbidden. So we have to use auxiliary field, auxiliary level to bridge the transition. That takes a lot of time. Now, if you can directly drive the transition, it will be much faster. That's one way to do it. Another way people have been studied is if you use, actually, I thought that's what I would do. When I proposed to Chris Monroe for joining his group, I was like, man, I have experience in high power laser. Even though in the bottom of my heart, I was like, please don't make me touch high power laser anymore. I hate it. But I was saying, people are doing high power laser driven gates. So it's like 5 femtosecond laser, really high power laser. It's just because the sheer power is in there. I don't know if you guys have ever used high power laser to heat stuff. If your hand is hit by a high power laser, it felt like you were being punctured by a needle. It's not like a burning. It's like a high energy, high momentum that is directly punching onto your hand. And we talked about that gate being driven by the laser is involving those motion, right? So imagine you have such momentum kick to the ion. You can induce a lot of information and energy onto it in a very short period of time. That's what allow you to drive very fast gates. So I was just talking in a very hand-wavy way. So if you're interested, look into that. There are more scientific way to put it. But this kind of high power pulse laser drive is also another way to do it faster. What is the main challenge to achieve scalability in ion traps? For example, the difficult of shuttling technique. Yeah, thanks for having the bracket there saying, for example, the difficulty of shuttling technique. Because Chris Monroe, our founder, my mentor, my PhD mentor, once said, ion trap technology is great because all the science is being figured out. All you have left is engineering challenge. Man, but there is really engineering challenge at every front, right? For example, sending people to Mars is also an engineering challenge, right? What are the science we don't know about there? We know everything about the science, but have we sent people to Mars? No, we haven't, right? Even though the richest man in the earth has been trying as hard as he can, I heard he's even giving up. So, it's very hard. Yeah. Okay. So what is the difficulty of the shuttling? There's challenge everywhere. So specifically, what is the difficulty for the shuttling technique? I think the biggest challenge for the shuttling technique is to do ion trap computing very well. You have to control the motion very well, right? The gate is done by shaking the ion, right? If your ion is already shaking, what's the difference between shaking them or not, right? There's no difference if they already shake. So you want to minimize the motion of the ion to begin with, meaning you want to make sure their motion is very pristine. We more or less figure out how to do that if we have a trap and the ion stays there. But now, once you want to shuttle them, once you want to move them, that's a different. Imagine you have a box with a metal ball in the middle. How do you move them? How do you move the box from here to here with the metal ball in the middle don't move? That's very hard, right? Even you do it by hand where you can see, it's very hard. So shrink it down to an ion scale, it's also very hard. So that means shuttling it many times would induce extra disturbance to its motional state. In my opinion, it's the biggest challenge in that aspect, the way I see it. Next question, is there a limit to the number of qubits in a single ion trap chain to preserve all-to-all connectivity? And if we connect multiple ion trap chip, is all-to-all connectivity preserved? No. Yeah, there is a limit for the number of qubits you can have in a single chain. I will not give you exact answer because IonQ typically don't like that kind of answer. I mean, if you look into literature, I'm just referencing literature, not my opinion, just referencing literature. You will see people start to observe weird effect once you start to have like 80 qubits, 60, even go beyond the 60. If you want to talk with ion on the two edge of the chain, it starts to become difficult. And what is that difficult come from? It really ties to how the ion gates are performed, right? You remember this picture we have on the Newtonian cradle. Jesus, that's such a long rewind. Okay, yeah. So what this does, you can think it as a pulse or a wave or a ripple that go from one edge of your chain to another edge of your chain, right? The physics behind it is really no difference than if you drop a stone into a pond and you see the ripple goes from in the middle that travels across the water, right? And if you pay a little bit more attention, you will realize the ripple will broaden as it travels across the water. This kind of effect is known as diffraction. Diffraction is common everywhere. When you have motion like that, when you have wave, you have diffraction, right? And diffraction is essentially what's going to dissipate your information. So, so when you have a chain of ion, when the chain is too long, the information will suffer from the same effect when it goes from one end to another. So yeah, we typically have to limit the length of the chain and switch to photonic connection. If you select to photonic interconnect, then it's not auto-connected. The ion, the information has to go through those ions that are connected to the photon like link to go to another trap onto only those ions that are connected by the fiber. Yeah. How can we construct integrated optics necessary to build an ion trap on a single chip? What should I study to prepare for this? Oh man. I don't know how can we construct integrated optics necessary to build an ion trap on a single chip. Integrated optics. Oh, well, there's a lot of things you can do. Integrated optics have some issue, like fabrication issue, have like a charging issue. I think most of that, I think it's a domain, it's a subject, a field called integrated photonics. I think if that's what you're interested, any study you do in that integrated photonics field can be translated to this, right? And at some point, if you don't want to do that, you can go to maybe, if you're into AR lens, right? The Meta just recently released like the device, smart glass, you can put on your face and you can see the image. The reason you can see the image is because they have many integrated photonic devices on the chip, on their lenses, right? So it is really a magical, powerful technology that has many, many applications. So I would think I would have fun doing that, I think it's really good direction. Is there a roadmap for constructing high-dimensional QLDPC code or other QEC technique for early fault tolerance? That's a good question. Let me first admit I don't have that strong expertise in fault tolerance, but I also don't know if we have ever announced any roadmap for quantum fault tolerance. First, of course, we have our internal error correction roadmap. I just don't know if it's released. Yeah, I guess I would just say that much. Although ion trap has a 530, it is still inefficient to solve commercial algorithm as, yeah, sure. We don't have enough resource to solve Shor's algorithm for RSA 256. I think that would require actually, and most people think to solve to perform Shor's algorithm for meaningful scale, meaning a scale that can crack currently being used RSA protocol. it will require fault tolerance of like, I don't know, the number may be off terribly, but certainly larger than 1,000 qubits, or certainly larger, maybe even larger than 5,000 qubits, right? You said you were going to connect multiple, next question. You said you are going to connect multiple ion trap system with photonic interconnect. Is it possible to do things like entanglement? Yes, yes. You can use fiber to conduct classical information. If you are thinking of entanglement, the information you conduct has to be quantum, right? And in that case, what you really do is you can think you are doing a quantum gate between a qubit, between an ion qubit and a photon qubit. So that information passes as your, so you have the capability to do gates between ion and photon, and the photon between an ion, right? And if you look into this thing called teleportation, you know you have a way to teleport, to make entanglement between two qubits and pass information from one to another. So in that case, you just have to use this teleportation protocol to move one state from your qubit onto your from your ion onto the photon, and from the photon back onto the ion. Then you can create the entanglement between two chip, and that has been demonstrated. Yeah, when people claim, when people want to show they have created the photonic interconnect, they always have to do this thing. To typically they would probably do some simple Bell test, not loophole free, because loophole free Bell test is very challenging, but to do some simple Bell test to show that the entanglement is playing a role in there. The ion seems to be aligned in a straight line. Can they be topologically shaped? I don't know what you mean by can they be topologically shaped. Do you mean can they be, I guess you mean, I mean, okay, in principle, they can be shaped into many, many different configuration. The easiest way to do is to shape them in some kind of lattice, right? The real reason why we do it in a straight line at this point is really just because the laser goes in a straight line, right? So if you put them in a straight line this way, you can shoot your laser this way, right? But now we are shifting towards this microwave wire mode. So the real microwave wire can go any way it wants. So you're not limited by this. So you're not limited by this. So there are many designs that plan to trap the ions as a 2D array or something, you know, very much like superconducting qubits on a trap. But the motion is shared among all the qubits in this 2D array, so it's still all to all connected as long as they're on the single trap. Yeah. Okay, that seems to be a last question. Any other thoughts or questions? If not, I'll pass the mic back here, guys, to the official. Sounds good. Thanks again for having me. It's a great venue. Yeah, appreciate it. So enjoy your guys' Saturday. Yeah.